Let's talk about one of the best problems you can have in engineering, but also one of the hardest. Your application is a hit, it's taking off, but now, how in the world do you scale your database to handle all that success? Let's trace that journey from a single overwhelmed server to a truly resilient distributed system.
So let's imagine this. Your app is a massive success. Users are pouring in. But there's a dark side. That single database that was humming along just fine a few weeks ago, it is now on fire. Response times are crawling, users are getting frustrated, and the whole thing just feels like it's about to fall over. This is the price of success, and it's a problem we absolutely have to solve.
And this brings us right to the heart of the matter, the scaling problem. How do we give our database more firepower to handle a constantly growing number of users? There are really two main ways to approach this. Now, your first gut reaction might be to go for vertical scaling, right? Let's just buy a bigger, badder server. More CPU, more RAM, more everything. And you know what? That works for a little while. But you very quickly run into a hard limit. There's only so big a single machine can get, and the costs just go through the roof. The much more sustainable long-term path is horizontal scaling. Instead of one giant machine, we add more smaller machines, and we spread the work across all of them. And that right there is where sharding comes into the picture. Sharding is really the main strategy for scaling a database horizontally. The idea is simple. We take our one massive database and break it up into smaller, independent pieces called shards. Each shard holds just a slice of the total data, which makes the entire system way more manageable and ready to grow. Okay, so how do we actually split all this data up? I mean, we can't just throw data at servers randomly. We need a clear, consistent system that tells us exactly where every single piece of data is supposed to live. And this leads us to what is, without a doubt, the single most important decision you'll make when you're sharding. That all-important decision is choosing the shard key. The shard key is basically the compass for your data. It's a specific column in your table, something like a user ID or maybe an email address, that the system uses to figure out which shard that row of data belongs to. And let me tell you, choosing the right shard key is everything. If you get it right, your system can scale almost infinitely. Get it wrong, and you've just created a performance nightmare. So, what makes a good shard key? Well, it really comes down to three key things. First, you want high cardinality, which just means it has a ton of different unique values. Second, you need even frequency to make sure the data is spread out evenly. You don't want hotspots where one shard is doing all the work. And third, you want it to be non-monotonic. This means the key doesn't just increase over time, which would cause all your new data to pile up on a single shard. Now, there are a few ways to use this key. You could use something called range-based sharding, putting users with last names A through M on one server and N through Z on another. But a far more common approach, and the one we're going to dig into, is hash-based sharding. And on the surface, it seems like the perfect, elegant solution. The logic here is it's beautifully simple. You take your shard key, you run it through a hash function to turn it into a number, and then you use the modulo operator. That formula, hash of key mod n, where n is just the number of servers you have, gives you the remainder. And that remainder tells you exactly which server the data goes on. It's clean, it's deterministic, it spreads the data out perfectly. I mean, what could possibly go wrong? Well, as it turns out, that simple, beautiful solution has a catastrophic hidden flaw. And it's a flaw that only rears its ugly head when you try to do the one thing you set out to do in the first place: scale. So, picture this. You have 4 servers. Your n equals 4. Your data is perfectly distributed thanks to that simple modulo formula. Everything is running smoothly. Queries are fast. The load is balanced. You're probably feeling pretty good about yourself. You've solved scaling. And then the inevitable happens. Your app keeps growing, and you need to add a 5th server. Or even worse, one of your servers fails, and you're suddenly down to just 3. What happens to our neat little formula now? The value of n is changed. And this is the moment where everything falls apart. When n changes, say from 4 to 5, the result of that modulo operation, it changes for almost every single key in your entire database. The home for nearly every piece of your data has just been instantly reassigned. This disaster has a name. It's the dreaded rehashing problem, and it is a data migration apocalypse. The second you add or remove a server, you trigger this massive, system-wide reshuffling. Every server is desperately trying to send data to every other server. Your application basically grinds to a halt. Your elegant solution has just created total chaos. But okay, don't panic. There is a much, much more intelligent solution to this problem. It's an incredibly elegant answer, and it's called consistent hashing. So, what is consistent hashing? It's an algorithm that does the same job of distributing data, but it does it in a way that doesn't completely freak out when the number of servers changes. Its entire purpose is to minimize the amount of data that has to get moved around when you scale up or down. The way this works is really cool. I want you to imagine a circle, or maybe a clock face. This circle represents every possible hash value. Now, using a hash function, we place both our servers and our data keys at different points on this circle. To find out where a piece of data belongs, you find its spot on the circle, and you just start walking clockwise. The very first server you run into, that's its home. And this is the magic part. This is the payoff. Now, what happens if a server is removed from the ring? Well, only the keys that were assigned to that specific server are affected. They just continue their little clockwise walk until they find the next available server. And all the other data, all the other keys on the ring, they stay exactly where they are. The data migration storm has just been reduced to a tiny, predictable trickle. No more chaos. Now, this is a massive, massive improvement. But there is one final piece to the puzzle, one more refinement we need to make this approach truly robust and ready for production at a huge scale. You see, this basic model still relies on a little bit of luck. A random hash function could, just by pure chance, dump 3 of your servers really close together on the ring. And if that happens, one server ends up being responsible for a huge arc of the circle, while others get just a tiny little sliver. We'd be right back to having an unbalanced load and dreaded hotspots. So we still face these 2 potential issues that are just rooted in randomness. The servers might not be spread out evenly on the ring, and the data keys themselves might not be perfectly distributed either. We need a way to smooth out these statistical bumps in the road. And the solution is a really clever trick called virtual nodes. Instead of placing server A on the ring just one time, we place it on the ring hundreds of times. We create these virtual points, server A-1, server A-2, server A-3, and so on, that all point back to the same physical machine. By doing this for all of our servers, we use the law of large numbers to basically guarantee a much, much more even distribution around that ring. It effectively wipes out the hotspots caused by random clustering. So, when you boil it all down, we've gone from a simple modulo formula to a more complex system with hash rings and virtual nodes. And yes, it absolutely adds engineering complexity, but for any system that needs to operate at a large scale, that trade-off is the absolute key to unlocking real scalability and reliability. It's what allows a system to grow gracefully instead of collapsing under its own success. The real question isn't if this is a good idea, but at what point does your system need to make that leap?